All right, Amy, you are all set.
Okay, so what we're going to do, if we could save all the questions until the end, because what I was telling Clinton is that I'm going to try and squeeze in 3 weeks or more of ground school into an hour. So let's, of course, everybody's muted, so it really doesn't matter. But don't raise your hands and flag at me because I'll ignore you. But so we're going to talk about just the basic aerodynamics, but we're going to hit on a bunch of stuff. So first of all, I think Clinton will enjoy this. This is how airplanes actually fly. A lot of magic. Okay, so this is what Steve sent everybody an email, and there are 4 forces that act on an airplane. That's the basics of aerodynamics. And thrust is the engine. So whether it's a jet engine, which that just functions like a squid going through the water. And then there's drag, which is the opposite force of thrust. And drag is basically the taxes that we pay for flying through the air. And we'll talk a little bit more about that. There's weight, which is gravity. So if there were no gravity, we wouldn't have weight. And that's just the weight of the airplane and the people inside, etc. And lift. Now, lift is the most important of all of these. They're all important, but lift is the most misunderstood, and it is the one that's the most complex. So we're going to talk mostly about lift. We're going to get into center of gravity and weight at the end. We're going to talk about thrust a little bit with propellers and how they act as airfoils, and we'll talk a little bit about drag. So we'll go on to the next slide here. So what is thrust? And I already basically explained that. That is the mechanical force generated by the engines or your engine to move the aircraft through the air. So in the radio controlled airplanes, you have the motor, which is spinning and it's turning a propeller, whether you're using a gasser, as you guys call them, or a battery operated. You have a propeller that's being turned by the engine. So that's creating thrust. And then drag is, once again, that's the taxes that we pay. It's parasite drag, which is the antennas, the body of the airplane itself, and then there's induced drag. And induced drag that's because we're creating lift, then we're also creating drag. So that's the most simplistic way of putting it. One thing that where this is going to be available as a PDF after tonight, and I'll have you can go on NASA's website. I have a bunch of links where you can click through and you can look at all of these more in detail and how they function. And if you want to do the coefficients of lift and all that, if you really want to geek out. Weight, once again, that's the gravitational attraction to the Earth. So, okay, lift is a mechanical force generated by a solid object moving through a fluid. And everybody says, well, the air is not fluid, but we need to get to the basics. So air is a fluid. It can be compressed and expanded. And like liquids, which are called hydrodynamics, air or aerodynamics is affected by the Coanda effect, Venturi, which is also Bernoulli's principle, and Newton's laws of motion. There's 3 of the Newton's laws of motion, and mainly we're dealing with a third. For every action, there's an equal and opposite reaction. So let's look at the Coanda effect. How many of you drink coffee and you get really ticked off when you pour coffee out of the coffee pot and it flows over? It wants to flow. Or if you're pouring liquid out of a cup, it wants to flow over the edge of the cup. So let's look at that. Because air is a fluid, it utilizes the properties of the Coanda effect. And that is the tendency for a fluid to follow the object along its flow path. So let's see if this will work real quick. Are you seeing the Coanda effect now?
No,
No.
unfortunately, we're not.
Okay. So what the gentleman does, and once again, you can go back to that screen. You can click on this afterwards. We're going to give you the PDF. What happens is that he does an experiment where he hangs a spoon from like a stick, and he has it next to water. And where let me get a piece of paper. Where the spoon is bent like this, okay, so this looks familiar. This is the wing of your airplane, if you look at it from the side. He takes the spoon and has the spoon edge, the bottom like this, and it sticks to the water. So you guys can watch that afterwards. If you turn the spoon around and you have it like this, it doesn't stick to the water. So that's what we're looking at on an airfoil is the wind, the air comes up and over and it sticks to the surface of the airfoil on top. Does that make sense? I'll just take it from Doug here. Okay, then we're dealing with Bernoulli's principle, which is basically Venturi. And I just want to tell anyone in the future who's watching this video who might be an engineer or work for NASA that their lift is, there's many theories on lift. I'm teaching you the flight instructor version, which is oftentimes people say, no, the Venturi has nothing to do with it because the wing's not a Venturi. However, what happens with the wing is, if I can show you here, I'll use a pen. So what Bernoulli did, Daniel Bernoulli took water and put it through a hose. So you can see the hose right here. And what he did is he applied dynamic pressure to the outside. And he put a pressure a thing to measure pressure up on top of the hose and found that the static pressure was lowered where the water molecules sped up. So with the wing, we're dealing with this Venturi of, let me draw a wing here. So we're dealing with the airflow going faster over the top, slower over the bottom, and creating that low pressure here. And once again, you have people saying no, but we also have, let's see what I can do here. But that's what we teach. So we have the Coanda effect and then Bernoulli's. And here is a better picture of Bernoulli's. Increased velocity equals decreased static pressure. And so here we have the wing, and the wing, here's the air coming in from this direction. And it goes up and over the wing, and it's moving faster over the top, which creates the lower pressure, which creates lift. And then we're going to get into Newton's, which is the bottom of the wing. Okay, so Newton's laws of motion, mainly we're dealing with the third law. For every action, there is an equal and opposite reaction. So the motion of lift, and you'll be able to click on this to go to NASA. The motion of lift from an airfoil, the air is deflected downward by the airfoil's action, and in reaction, the wing is pushed up. So we have higher pressure under the wing, lower pressure on top, and it's causing that wing. We'll go back to this. We'll go back to this one. And so now we're dealing with Newton's laws of motion down here, pushing it up. And this will take you through, NASA's website is great for, especially if you guys have kids or grandkids that are coming out to fly. Their website has different grade and age groups, and you can do different projects with the kids. So the Kawanda effect, you can do, there's all these projects that you can do with it, and lift, weight, drag and thrust. Okay, so for airfoil terminology, this is if you take your wing and you cut it. Are you guys able to see my mouse pointer here? Okay. Okay. So this one is we're in a climb here. Here's the leading edge. That's the term for the front of the wing. And we have the trailing edge. Now we look at the shape of the wing, and the wonderful engineers figured out that needed to be the shape of the wing, that it had a higher camber on top, more camber, and less camber on the bottom. Now, some of your planes are going to be the same or almost flat. And the reason that they're designed like that is because they're aerobatic. So they're able to fly upside down as well as they are right side up. So this is a normal wing that's going to create lift right side up. And we're going to talk about stability later. This is a very stable airfoil. Okay, so the wing is called an airfoil. If you look at your propeller, it is also an airfoil. It is shaped exactly like a wing. The elevator on the back that makes the plane climb and descend is also an airfoil. And the rudder, which makes the airplane yaw back and forth, the plane yaw back and forth this direction, is also an airfoil. And they all have the same concept. But let's talk about just the wing here. So I've got some definitions down here. The relative wind is the wind just coming across the ground. It's just goes right along the ground all the way up. And it's here we've tilted the wing up. And so we have what's called an angle of attack. And the angle of attack is how much you're climbing or descending. So you could have a negative angle of attack, which would be descending. You can have a neutral angle of attack, which would be straight and level. And you can have a positive angle of attack. And that's what we see here. And this is a climb. So if you look at this airfoil, you can really see, get my pen out again, how this, here we got the air molecules coming over the top, and then we have the bottom. So this is what we were talking about with Bernoulli's and then with Newton's laws of motion. So these air molecules up here, lower pressure along here. Okay. Go. Okay, so an airplane doesn't stall when the engine quits. That's just, where do I land? An airplane stalls when the wing stalls. So we want to look at angle of attack again. And that's the angle of attack is the angle between the chord line and the relative wind. So if we go back to our former one, the angle of attack is here. So here's our relative wind, and here's our chord line that goes right through the center of the wing there. So that's the angle of attack. And we want to know when an airplane stalls. Well, we've talked about lift. It stalls when we've raised our nose so high that now the wind is not, the air is not creating that low pressure. It starts breaking up. And so here we have just a normal angle of attack. Here we have a high angle of attack on the left. Now we've what we call exceeded the critical angle of attack. So the airflow, we still have the airflow along the bottom. That's great. But now we're starting to get this breaking up. And there's on the next one, this slide, this YouTube here actually discusses stalls, and it shows the they put ribbons or strings on a wing, and they fly it, and then they stall the airplane multiple times. And what happens is the plane is designed to where we call this the wing root, right in by the fuselage. And the wing, this is where it stalls first, is in the wing root, and then it moves out here. And that's because the designers want you to be able to use your ailerons as much as possible. So one wing will stall before the other wing. I love this picture because this shows, this is in a wind tunnel. And this actually shows, here's the air going over the wing, normal. And here we have the breakup. So what happens, if you haven't experienced this out there yet, this would be a good thing to do, is to get altitude, climb up, and purposefully stall the RC airplane. And what's going to happen is they don't stall at the same time. So what'll happen is you're going to bring the nose up, bring the nose up, bring the nose up, and one wing is going to stall before the other. So you'll have a dropping motion. And what you're going to do to recover is to lower the nose, and you put in the rudder on the high wing. So I'm not sure how that works with the transmitter. In our airplane, we call it stepping on the high wing. So I would imagine on your transmitter, you'd probably put in right rudder then. So bring that back down. You lower the nose to break the stall, get the air flowing back over the wings, and then the rudder, the ailerons are no use anymore. So if we start using ailerons to recover from a stall, that's when it goes into a spin. And it would just go straight down and do this, which I think some of you guys do that for your aerobatics anyway. So, okay. So that's what a stall looks like. And it's just going back to those principles of happy molecules. We have low pressure, everything's going over the wing great. We've now exceeded that critical angle of attack. And so that wing is going to stall, which means it's just going to drop. And we're going to get into stability in a few minutes. All of this is aircraft design. So they've designed your remote control airplanes or radio controlled airplanes, and they've designed full scale airplanes to where they want to fly straight and level, where the four forces are equal. So we talked about lift, weight, drag, and thrust. They want to fly straight and level like this. So go to the next one. Okay, so the aircraft axes, those are, we have longitudinal, which is our banking motion or rolling motion. And we use our ailerons for that. So let's look at those ailerons. I'm going to put, our ailerons work opposite of each other. They don't work together. So you would never see ailerons like this or like this. That's flaps. So we're going to have one that's going to be up and one that's going to be down. And this airplane now is going to bank this direction because we have more lift being generated by this wing. So we're going to bank, and that's the longitudinal axes. Now we have the vertical axes, which is controlled by the rudder. And the rudder is back here. This is the vertical stabilizer, has the rudder portion in it, and that's where we get into yawing the airplane. Then we have the elevator, and the good way to remember the elevator is elevators go up and down, and the elevator is the lateral axis is for pitch. So then we have the airplane pitching up and down. If we lower the elevator here, it creates more lift. So the tail of the airplane comes up, and that means the nose is going down. If we bring the elevator up, it creates more drag. So the tail is going to be down and we'll be climbing. So once again, going back to these are airfoils, and it's working the same way as the wing with Bernoulli's principle and Newton's laws of motion and the Coanda effect. Oh, and the center of gravity is right smack dab in the middle of those axes. So that's super important. If I don't know if any of you guys have taken off and had your battery move, but that's when you know that your center of gravity is off. So we'll talk about that in a minute too. So the center of gravity is right in the middle of all of the axes. Okay, so banking turns, we have this elevator, or I'm sorry, this aileron is down. So once again, this is the way they have it. So they have the left aileron down and they have the right aileron up. So the right aileron now is creating drag, and the left aileron, because it's down, it's creating lift. So we're going to be banking to the right, like they show here. Now, one of the problems with creating lift is we create more drag. So it's just those taxes that we pay for more lift. We're going to have a little bit more drag. We're going to talk about that in a minute with when the airplane yaws. Okay, now he's turning the opposite direction. So now we have this aileron up and we have this aileron down. So now we're going to be banking this way. We have more lift on this wing and we have drag on this wing. So the plane's going to bank like this. And you can see at the bottom here that we're dealing with when you put that aileron down here, you have more camber, greater angles. So the molecules are coming over here faster. Molecules are coming over here and hitting. So this is creating drag on this side, and this one's creating lift. This one's creating lift over on this side. And here we're straight and level up at the top. We have equal lift. Okay, so now we're getting into, well, that's great. This left wing, the aileron is down, and this one, the aileron is up. So we're going back to this again. And so this plane, we have more lift because this aileron is down. It's going to be banking this direction. But what also happens is then we have what's called, or we have a vertical component of lift. So the plane's happy as it's going along. It starts banking, and our vertical component of lift starts going out to the side. And so we actually have almost a horizontal component of lift. And now we're going to be getting into, so we have the horizontal component of lift. Now we're going to be descending. The nose is going to want to drop. So what we have to do is to give it back pressure on the elevator. So we have to raise the nose by moving the elevator up. Okay. So we've talked about the elevator. The elevator is meant when we're banking. If we're going to climb or descend, we use the elevator. That's back here. If we're banking, our vertical component of lift starts going out to the side. So we're going to have to raise that nose or give the airplane more thrust. We can always add more power to bring that nose up as well. So either one. In the planes that you guys are flying and that I'm flying, we have left turning tendencies, and this is where we're going to get into the rudder usage. So the first one is torque reaction, and that is the motor in the planes. So the motor and the propeller, got my pointer over here, they are spinning to the right, And so with them spinning to the right, they're wanting to force the nose of the airplane to the left. So now what we're going to do is we're going to use right rudder to bring the nose of the airplane straight. So that is one of the left turning tendencies. The second one is precession, which is here. So the force and the action. And then we have slipstream, which is the air is coming this direction and is coming around and hitting the left side of the plane. So that's slipstream. And then we already talked about the ascending left blade and the descending right blade, which is also going to shove the nose to the left. So that's where we start using the rudder here in the vertical stabilizer. And we have to yaw that, we have to bring the airplane back with right rudder. And that usually happens mainly on climb outs. Straight and level, you're not really having to use the rudder that much. Banking turns, you're going to need to use the rudder. And you really feel it in a full scale plane. You start getting people sick in the back of the plane if you're not using the rudder correctly, because you'll start skidding and slipping as you're going through the air, and it just gets real bad motion back there in the smaller planes. Okay, and then we have adverse yaw. So we talked about the taxes that we pay we have lift, and there's the tax of drag. That the more lift we create on this right wing, then we're going to have more drag on that wing. And what happens is then we have a yawing motion. So we have to use rudder for that also. And it's just called coordinating a turn. This is the way I like to describe ailerons and rudders. Rudder. The ailerons are the first fire truck driver, and the rudder is the guy in the back here. So this gentleman or woman, this firefighter, is turning the fire truck, and this person back here has a steering wheel and also turns so that these tires aren't skidding or slipping back here. So thinking of the first fire truck is the aileron, and the ladder section is the rudder. That's the easiest way to remember that. And they're just used together. This is going to be for future use. It's just you're going to be able to go back in here. Unfortunately, you're not seeing it when I click on it, but this is where where you can really geek out. You can use vector quantities and all the fun stuff. And that's on NASA's website. Okay, so maneuverability, controllability, and stability. Maneuverability is the ability to change attitude and withstand stresses. Controllability is the aircraft's response to pilot inputs. And stability is this, we're going to talk about stability, the tendency to correct back to the original state. So we talked about the camber in the wing, and the ones that have a real high camber, a lot of camber on top of the wing and less camber on the bottom, are a more stable wing. And so they're always going to want to go back to their original state. We have static stability, which is the aircraft's initial response. And then we have dynamic stability, which is over a period of time. And here's what it looks like. So we have straight and level flight. Then we have a plane that now we're going to pitch up by using the elevator. And this plane is going to become statically unstable divergent. And that is the worst plane to be in as a pilot. So what they do, we're getting into fighter jets tend to be unstable because they want to get rid of as much drag as possible. And so they're designing them with swept forward wings. They're designing them with less camber. So they're the ones that you have to fly it all the time. With this plane, we have a neutral static stability on the bottom. So we disturb the plane, and it just continues in that same disturbed state. And the one at the top is the one that we want. We want to be able to disturb the plane, have it come back, disturb the plane, have it come back. And what I say is, once you're in straight and level flight, a monkey can fly a plane, because if you put it in a bank and then bring the ailerons back to neutral, or the control yoke, or your transmitter, that plane is going to want to come back to be stable. When you're getting into more of your aerodynamic planes that you guys are flying out there, when you move from, let's say, the Apprentice to one of the faster planes, their wings are shaped different, and they're made so that they can fly upside down. So those planes are going to be they're going to be less stable. Okay, wing dihedral has a huge effect on stability. If we're flying the high wing airplane, we have less dihedral. And in some of the planes that are like Air Force planes, their wings actually come down. They're swept down or swept back. Those have a lot of what's called anhedral, which is at the top. Super unstable planes, but they're fast. So the high wing airplane, this would be something like a Cessna, or for you, this would be the Apprentice. The high wing airplane is a little less stable. However, with your Apprentice, if you look at the side of the wing, it has more camber than some of the other airplanes you're flying. And so it makes it more stable. So the low wing airplane has a significant amount. If the wing is shaped like this, sort of like a V, then there's a significant amount of dihedral on this and very little anhedral. So now we're looking at a wing that's far more stable, an airplane that's far more stable. Okay, so this has been coming up a lot. This is the book. There's a series of books that Don got for the school out at Palomar. And whoops, I can't touch anything here. This has become sort of a little bit of a controversy. First, I want to say that the author of this book his books are amazing, and he's keeping everything pretty simple. But I do want to address this page because it's been brought up a lot. So at the first part here, he's talking about a turn. And we're going to go to the pen here and circle this. So he says, immediately pull up elevator and hold it in to pull the nose into a turn and to keep the nose from dropping throughout the turn. The second part of his sentence is correct. The elevator does keep the nose from dropping, and we already discussed that. However, the elevator does not turn a plane. So that is the ailerons and the rudder. We've already looked at how the ailerons bank the plane and the rudder coordinates the turn. So if you can look at this page and just ignore where he says, pull the nose and do a turn, because it's really that's not happening. What we're doing is keeping the nose from dropping, which is what he says here. Okay, this was the other thing that has become like a topic of conversation, is when you're using your transmitter, or when I'm flying my plane, we would be banking. Once again, this aileron is down, this aileron is up. This one's creating more drag, this one's creating more lift. So the airplane's going to bank this direction. Now, when I roll out of my bank, I bring we call the steering wheel in an airplane a control yoke. So I'm steering this direction and I'm going to bring it back to neutral. I am not going to be in a 30-degree bank turn, overcorrect the other direction, and then bring it back to neutral, because what's going to happen is people are going to start throwing up. So we would have the plane like this, the plane would go like this. So that is, if you have my airplane, the Piper Comanche, is a low wing airplane that has a significant amount of dihedral. And we talked about dihedral. So let me go back to the arrow. What I say here, I put in this note, what he's talking about, he says smoothly apply aileron opposite the direction of the turn to return the wings to level. And I say that's only necessary if the airplane has very little dihedral, making it less stable, such as an aerobatic aircraft. So Don went out the other day because I was questioning this, and he tested it on the Apprentice. And when he banked the airplane, I don't know which way he banked it, but let's say he banked it to the left, and then he put his transmitter back into neutral, and the plane came back to neutral. Stable airplanes want to fly straight and level. And that's why I say a monkey can fly a plane, because it's going to fly through the air until you run out of fuel straight and level. So what Don did was he banked the airplane, brought his transmitter back to neutral, and the airplane went back to neutral. If he had banked it, then brought it back the other direction, it would have rolled the other way. So that's why we talked about stability before we opened up this page. The aerobatic airplanes, some of them will be less stable. They'll have less dihedral, and then you will potentially have to correct the other direction. So that'll be a fun thing for you guys to practice with out there. It's just, I know that this has been coming up, and when Don came home and said that, and Don's an instrument rated pilot, so he's been through quite a few courses for flying. It didn't make sense to either of us. So that's why I wanted to bring that in here. Once again, at the bottom of here, the author says, ailerons bank the airplane, up elevator turns it. So we want to just dismiss this, because ailerons bank the airplane, which is turning it. The rudder coordinates that turn. The elevator just keeps the nose from dropping. So the elevator does not turn the plane. So if you could just ignore this verbiage. Once again, the author, throughout his books, it's amazing what he's written, and he's done a fantastic job. And the graphics, I think I could even fly an RC airplane if I use these with the graphics. So every book, unless you get it from the FAA or NASA, there's going to be something in there that's, that we want to look at, we want to question it and say, is that aerodynamically correct? And it's not. Okay, center of gravity. We talked about how we have our axes of the airplane, and in the middle of those axes is the center of gravity. So the center of gravity is, in the RC airplanes, you want to have it where the airplane is going to be able to hold like this. It's not going to fall forward. And if the battery's too far back, it's not going to go like this. And you're also dealing with just plain weight. In an airline, in my airplane, center of gravity is super important, because we're dealing with fuel that's being held in the wings. So as the burns, we're dealing with a different center of gravity when we land the airplane than when we take the airplane off. So we plan our center of gravity before takeoff and on landing, by how much fuel burn we have. So at the bottom here, I made it applicable to you in that the battery placement in the RC airplane is important as it affects the CG, which in turn affects takeoffs, landings, and stall recoveries. These are links. You can come back and look at these more in detail. And once again, they're part of the NASA website. So here we have a really good graphic on this center of gravity is too far forward. Let's say you put your battery up here farther in the nose. And what is going to happen is that then you'll have, now we're going to talk about the real usage of the elevator. You'll have insufficient elevator nose up force. So if the CG is too far forward, there will not be enough elevator nose up force to flare the airplane for landing. So we would not see the shadow here. You would not be able to bring the nose up, which back here, you'd be putting lift back here, or sorry, drag. You'd have drag back here on the elevator. You can see how the elevator's up, creating drag here, which is going to lower the rear end of the plane and bring the nose up. This is what's moving, not this. The elevator is making the tail more drag on the tail, which is slowing, bringing that down. If our CG is too far forward, we have too much weight there. We can't, our elevator's not big enough to be able to overcome that huge battery in the front. When this is where it becomes deadly for pilots in full-scale airplanes. If the CG is too far aft or too far towards the back, there might not be enough elevator nose down force at the low stall airspeed to get the nose down for recovery. So we've exceeded the critical angle of attack here. Now we've lost lift in the wing, and we don't have enough elevator back here to get that nose down. In other words, bring the rear end of the plane up. And that's deadly. If we take off in this plane with this configuration, that plane could go straight nose up like this, and there's no way to recover because the elevator's not, it doesn't give you enough lift or drag to be able to get that nose down. So there we're dealing with the correct usage of the elevator. And now we're going to talk about flaps. So on here we have the ailerons, which are on the outside of the wing. Some of your radio control airplanes have flaps, and you have the transmitters that have the ability to do the flaps as well. So the flaps we have flaps on our airplane. What the flaps do is they allow a plane to fly slower and have greater lift over those wings. So we can put the flaps at 10 or 15 degrees, 20 degrees, 30 degrees. There's usually 3 settings for flaps. The most I've seen them go up to is about 40 degrees of flaps. So they go down significantly far. If you look here, we have full flaps, and this plane is able to come in really slow and land practically right here. I mean, you could land right on the numbers, just coming nice, and you're not speeding up because you've got all that drag and extra lift. Without flaps, the landing is going to be a longer distance. And so that's for the landing point, and same on the approach. With full flaps, we're able to come in at a steeper descent angle, and the concern is speed. So we're going the same speed here as we are in this flat descent angle, because we have the flaps in, we're able to slow it down. A lot more drag. And then this video it's a good YouTube on that. Okay, trim is super important. Don wanted me to bring this up. If you're flying around, why fight the airplane? For me, I trim the airplane up as soon as I can, and we have we have the rudder trim on our airplane. Most importantly, we have elevator trim. And the elevator trim will keep the plane from climbing or descending, or it will, if we want to just trim it up for a nice slow climb. If I'm in the clouds and I don't want to be pulling on the control yoke or you on the transmitter, you just can have it in a nice climb by trimming out the elevator. And then before takeoff, once again, for pilots in full scale airplanes, this can be deadly. It's part of our checklist. We check our trim inside the airplane. Well, first we do a walk around outside, and then we check the trim inside the airplane with the levers. So if the trim is off, and if it's nose up, which would make the tail, we'd have more drag on the tail, which making the tail go down, then what's going to happen is we're going to be in a nose up real high. We could even be like that on takeoff. So we want to make sure before you take off that you do a really good pre-check of the trim tabs to make sure on the RC airplanes that those are the way you want them before you take off. Okay, and then, so now we know that magic doesn't make an airplane. We just went. Okay, the last page is just an aerodynamics review. And it talks about, it has a video that basically covers what I've covered from beginning to end. So Doug, did you want me to share that last screen or?
That's entirely up to you.
Let's see if I can get it back up there. Did you see that? Can you see that?
Nope, we're just seeing your file folder.
Okay. Well, once again, you're going to be given given the PowerPoint in a PDF, and it will have the links to this. And the last video on YouTube is really good. So the last picture, then we're looking at all of our four forces. We're looking at our different parts of the airplane, etc. So, okay, it's 10 till 8. Did you want to do questions, Doug?
Sure, if anybody has any questions, that might be a good idea.
I've got a question or two.
Okay, David.
Hi, how are you? Nice to meet you.
Nice to meet you.
So my background is military F-15. I just retired as Captain of the American. So if you have a symmetrical airfoil, how does Bernoulli create the lift?
With the Venturi. You talking
Well,
about?
it can't be a Venturi because they're exactly the same shape on the top as well as they are on the bottom.
I don't understand your question.
A symmetrical airfoil is exactly like an PT-38, is exactly the same curve on the top as it is on the bottom. So even it's perfectly symmetrical. So Venturi, so there can be no Venturi.
So it's creating lift while you're upside down and right side up.
But it can't because they're exactly the same shape. There is no difference in pressure.
Okay, well, that's why I said there's many different, this is one of the controversial things about lift is, but this is what flight instructors teach. So we teach.
I know they do. There's a great paper called The Lie of Bernoulli. And what it goes into is what really creates lift is Newton's third law. And what will happen is that if you place the wing at an angle of incidence, even a half a degree, then you'll have, it'll be actually its force in force against the airplane. So for example, on an F5 fighter, it has a perfectly symmetrical airfoil and it's in perfectly line with the fuselage reference line. And it will go off the end of the runway at 200 miles an hour. So what they do is they hike the nose through pneumatics, they hike the nose strut 8 degrees, which is 13 inches. And then it raises the nose so that the air is hitting the bottom of the wing. And Newton is making that happen. Newton is about 85% of an airfoil, and then Bernoulli is about 15%. The other thing that I have is that on a symmetrical airfoil airplane, or even on a regular airplane, if you roll into a bank and don't do anything, it will sit there. The nose will drop, but it'll just sit there until you pull on the elevator. If I roll into 30 degrees of bank and step on the rudder, I will drop the nose down. So in fact, in fighters, the quickest turn that we make is we do an unloaded roll, and then we pull with the elevator, and there is no rudder whatsoever in it.
Okay, but I'm not flying fighter jets.
No,
So-
but I'm saying, but we have symmetrical airfoil aerobatics airplanes like the Next to
Right.
300, and it flies the same way. So if you roll that thing up, it'll hold. I just came back from 4 days of professional aerobatic training. And if you roll that airplane up on its side, it will hold that. Nothing will make that turn. It will descend. And if you put on rudder, it'll click it down. You can use left rudder and it'll fly off of the side of the airplane and it'll fly level if it's a big enough side force. But if you're in an airplane and you have a symmetrical airfoil and you step on the right rudder, the nose will go right. And then when you let go, it'll come back. I've actually done that on an Airbus as well as a 777. So now on a high wing trainer, like we have with Apprentice and the ones that you're flying. So you get some Bernoulli effect out of that, but the rudder coordinates the turn, whereas the elevator is what's pulling it around the turn. That's what I believe.
Yeah, no, we'll have to agree to disagree on that.
All right, because it's in that book.
That's why I'm teaching basic aerodynamics so that we can understand lift, the 4 forces and how they act on the airfoil.
I understand that, but in that book that you said is incorrect, he had said the same thing that I say. I think on our models, no matter what kind of wing they have, if you roll into 60 degrees of bank and step on the rudder to coordinate that bank, the nose is going to drop and the plane
Absolutely. The nose absolutely drops. And we talked about that with horizontal component of
But if
lift.
you roll into 60 degrees of bank, do not touch the rudder and pull with the elevator. It will pull the nose around. And if you pull at 2 Gs, it'll be a level turn.
Yeah, the elevator's not pulling it around. The elevator is bringing the nose up.
I disagree.
Yeah, okay, that's fine. So I've only been in flight instructing since 1992.
And I taught performance in the Air Force and have been flying since.
Did anyone else have questions?
Yeah, I'm here. Amy,
Hi, where'd Lanique go?
I don't know.
She got bored.
I'll give her a test later and see if she.
Okay. Okay.
Anyway, I've enjoyed everything and all the basics that you came up with. I've gone through them learning, and for me, it's going to help me a lot. So thank you.
There she is.
Here she is.
There you
So I'll give her.
No.
She didn't get us any ice cream for the show. No popcorn.
The popcorn.
Okay, well, thank you. Thank you. And like I
Very
said,
good,
this
very
is basic aerodynamics. I'm not getting into flying jets, etc. I'm applying what is basic aerodynamics. And if you look at the airflow over an airfoil, whether it's the propeller, the wings, the elevator, the rudder, they all function the same. They're all shaped the same, depending on what plane that you're moving into. And that's why we talked about stability as well. So thank you.
You did
Any other
great.
I
questions?
see that Clinton has a question there. Looks
Clinton,
like he's
can you
got-
unmute yourself? Okay, so did anyone else have questions? Oh, there you go. Clinton, did you have a question?
I just said thank you in the chat.
Oh, well, oh, there it is right there. Aw, to everyone. Clinton says thank you. Okay. All right. Your Mom
gonna
finished
go
dinner? Okay, well, you have a great night. Anyone else have questions?
No.
Fine.
No? There, Doug?
Yep.
There he is.
Yep, I'm here.
Okay.
Thank you, Amy, for doing all this. We really do appreciate it.
You're welcome. You're welcome. I guess we're right at an hour, so hopefully no one fell asleep and is drooling on their keypad. Because it can be a little dry. But once again, Rick Torres is going to make it available on the website. And the important thing about that then is you're going to be able to go onto NASA's website. There's all sorts of different ways that you can test out the various theories, and just be able to click on those links and watch the YouTube videos. So those are pretty cool.
Okay.
All right, well,
Oh, thank you, Mark. Thank you.
Amy. Great job.
Okay, thank you.
Thank you. Thank you. Bye.
Roll